Hi friends, we are on to Unit 2, and as you can see, it's about atoms in the periodic table, so we'll talk about what makes up an atom, a little bit about the history of the atom today, and then get into how the periodic table works and it fits together, and do some stuff with electron configuration, talk about how chemical reactions work. So where last unit was like a lot of math and calculations and stuff, this one won't be as much of that, but it will be a lot of maybe new definitions and new skills to help you understand how chemistry works and how the periodic table is put together and how we can use that to solve problems and predict trends and predict what will happen for reactions. Okay, so let's jump in. A little bit about the history of the periodic table, so you don't need to write these things down. But the modern chemistry is relatively young, just over 200 years old. It sort of was started, at least modern chemistry, by John Dalton. He developed an atomic theory in the early 19th century, and he believed that a few kinds of atoms made up all kinds of matter. And he thought that elements were like one kind of atom, and then compounds were made up of two or more different kinds of atoms. And he proposed this atomic theory. Again, no need to write this down, but the atomic theory was what sort of laid the groundwork for what modern chemistry is. And in his atomic theory, he said it had 5 points: that all matter is composed of extremely small particles called atoms, which cannot be subdivided, created, or destroyed. He also said that atoms of a given element are identical in their physical and chemical properties. Atoms of different elements differ in their physical and chemical properties. Atoms of different elements combine in simple whole number ratios to form compounds. And finally, in chemical reactions, atoms are combined, separated, or rearranged, but never created, destroyed, or changed. Pretty remarkable stuff for 200 years ago, when like the most advanced technology was like a microscope, basically. And all of it still holds true, except this part here at the top where it says that atoms cannot be subdivided, created, or destroyed. So that's the one part that has changed of his theory over time, as we have learned that atoms, in fact, are made up of smaller pieces like protons, neutrons, electrons, things that you've heard of, but even smaller pieces like quarks, muons, and things that were not really important for this class. But so we will get into what makes up the atom a little bit. I don't know why this is upside down. I'm sorry. So over time, just like any theory, more experiments lead us to refine the theory. And in the mid 1800s, the first person to change the atomic theory was that we found out that atoms could be broken down into pieces after all. We call those things subatomic particles. I don't know why it's at the bottom. And the three subatomic particles for this class are proton, neutron, electron. You probably already know all these things, so I wouldn't necessarily recommend that you write anything down right now, but that would be good to know that the three particles that make up the atom for this class that we'll talk about the most are protons, neutrons, electrons, but just be aware that there are much smaller pieces than that even that make up atoms, and they're finding out more about those as they smash all these elements together and stuff and do all these high-level experiments on them. Okay, so the first model, and I'm not really going to quiz you on like the names and dates and stuff, but just to give you a background, the first thing that was that really started to move things forward was called the Plum pudding model by J.J. Thompson, and that was a model where it was, if you could imagine like a ball of positively charged material, and then sprinkled in that were like the negative electrons. So kind of, I don't know if you've ever eaten plum pudding or like rice pudding. Maybe you can compare it to like cookie dough, where the dough part is the positive charge and the chocolate chips would be like the sprinkled in negative charge. That's what they thought the atom looked like for a while. And Thomson was the person who did that, and that was in England in the mid 1800s. The next experiment that sort of stood that one on its ear, or on its end, that was disproved it, was called the gold foil experiment, and that was done by Ernest Rutherford. And that experiment was just a few years later, and it disproved the Plum pudding model. And what it looked like was this setup where he had this radioactive material in a box, and he made a little pinhole in the box. And so as a result, the radioactive material shot out in one direction, kind of like a laser beam, but well before we actually developed real laser beams. And what Thomson did was he shot out this piece of gold foil here in the middle, and the gold foil is very, very thin. You're probably familiar with aluminum foil. Aluminum foil is ballpark 70 or 80,000 atoms thick. So 70 or 80,000 atoms like stacked on top of each other. Gold foil is much more malleable, which means you can like really flatten it out and really thin it out really well. And so gold foil is just a few hundred atoms thick, so many times smaller or thinner than even aluminum foil, which is pretty thin. And if the atoms really look like this, then what would happen is when the laser beam hit, it would just bounce back off, right? Because it's a solid ball. What Rutherford found out, though, was that in fact most of the particles went through the gold foil completely, and maybe they deflected a little bit, but they were all recorded on this part here. And then every once in a while, some of the particles bounced off in different directions, but for the most part, the atoms or the laser beam pew pew went right through. And so that was an experiment that sort of disproved the Plum pudding model and kind of gave us rise to what the atom really looks like. And so now we know, oh, this is fun, that the atom has a dense central portion called the nucleus. Inside that nucleus, you've got protons and neutrons. And these things you should write down. Protons and neutrons are, protons have the positive charge. So in the nucleus, that's where all the positive charge of the atom is. And almost all the mass, protons and neutrons are much, much, much heavier than electrons. But they're very small, they're very tightly packed in there. So the nucleus only accounts for a very small fraction of the atom. This is why only every once in a while did the particles bounce around and off in these different directions, because every once in a while the laser beam would hit a nucleus and then it would deflect the particle. But for the most part, the atom's actually empty space. And so as a result, most of the particles went right through. Okay. And then the electrons, they're on the outside of the atom, and they account for almost all the atom's volume. So they're very spread out, and so that they make up most of the volume of the atom, but almost none of the mass of an atom. That's because they weigh about 90,000 times less than a proton. So they really don't do much for the mass of the atom because they're so much smaller than a proton or a neutron. Okay, so those things you should have. And I just to like make sure it's very clear, this slide's kind of the same, but just to show you that protons have the positive charge, they're found in the nucleus. Neutrons are no charge, they're neutral, and they're found in the nucleus as well. And then electrons are negatively charged, and they're found outside the nucleus. If you ever like seen Jimmy Neutron or something like that, this picture is a pretty good model of what the atom looks like. It's has the electrons sort of orbiting, called the planetary model, where the electrons are these like little white circles here, and they're orbiting this nucleus, which is in the center. I mean, there's a whole bunch of problems with this picture. One of them is that the nucleus is actually much, much, much smaller. It's like a little pinprick where my mouse pointer is. So this is like way oversized here, the nucleus. But just to give you an idea, that's a decent model of the atom. This is why when Rutherford shot the laser beam through, like it would just go right through like that. Every once in a while, maybe it would hit the nucleus and bounce off in a different direction. But for the most part, it would just be able to travel right through, because most of the atom is actually empty space. So a good model to think of for now, if you're trying to picture in your head like what the atom looks like, is this is called the planetary model, where the electrons orbit the nucleus, and so the electrons are like the planets, and the nucleus is like the sun. You might be wondering, like, if you know anything about, if you took physical science, or if you remember physical science from middle school, these two things are attracted to each other. Electrons are negative, protons are positive, so there's an attraction there. But here you have a bunch of protons sitting very close together, and they should be not attracted, they should be repelled from each other. So what keeps them together? Well, one of the fundamental forces of physics is called the strong force. And the strong force is what keeps the nucleus together. Otherwise, because the nucleus is positively charged, the two protons, they don't want to be by each other, so they would explode outwards. But at very, very close distances, another force takes over called the strong force. This is like, strong force is essentially like gravity. It's one of the fundamental forces of physics. And that's what keeps the nucleus together. So the strong force between the protons overcomes the repulsive force and holds the nucleus together. Oh, that's fun. Okay. Let's move on. How we measure the number of protons, we call that the atomic number. You should have written down the atomic number on the periodic table. I'm going to get it wrong. I'm just going to say it's in the upper part. It's in one of the other upper corners of the each box for an element. So each element has its own unique atomic number, and it's the same for each element or each atom of that element. So, for example, the atomic number of carbon is 6. Every atom of carbon the atomic number is 6, and that means every atom of carbon has exactly 6 protons. The protons are what make the element, like, it's like basically the DNA of an element. What makes UU is what, for the analogous for an element, is that the number of protons is what makes the element unique. So you could, in a given element, you can add or subtract electrons, you can add or subtract neutrons, and still be called, let's say, carbon, for example. But if you are going to change the number of protons, now you're completely changing the element. It's not the same thing anymore. It has completely different properties. So, and so that each element has its own unique number of protons. No two elements have the same atomic number. Like, for example, carbon is 6, but if you shoved another proton in there, it'd be 7. That's nitrogen, which has a completely different properties compared to carbon. The atomic number of hydrogen is 1 because each nucleus of each hydrogen atom has 1 proton. If the atomic number of oxygen is 8, which means each atom of oxygen has 8 protons. You can add and subtract neutrons and electrons, and that will be the next lecture. And that's a thing that's very common for atoms. They can have different numbers of neutrons, different numbers of electrons, but it's that unique atomic number of protons that makes it the element what it is. Okay, this has been fun, and it's good to talk to you guys, and we'll see you soon. Okay, bye.